All right, thanks, Igor. So let me share my screen and let me know if you can, when you can see it.
Yep, it's perfect. Thank you.
Okay, yeah. All right, thanks again, and thanks you guys for inviting me to present some of these observations and insights from the HFTS projects that GTI Energy has been involved with. So, as Igor mentioned, my name is Dave. I recently transitioned to Progeo. I'm a senior engineer with Progeo Corporation, looking at essentially CCUS. But the presentation that I have for you today is based on some work that we have done in the past and still are doing with the HFTS-1 Phase 3 project. Uh, um, and the idea of this presentation is to just go over, provide like a kind of a broad overview of some observations and some results and some associated interpretation that we have done based on a lot of the data that has been collected at these test sites. So we have the hydraulic fracturing test site 1 project, which now includes 3 separate test sites, and the hydraulic fracturing test site 2 project in the Delaware Basin. So just to give a brief background on the HFTS program, this program, which has been seed funded by Department of Energy, was initiated with the primary objective of trying to essentially optimize unconventional completions and some of the plays that were in most demand at that moment in time. So the essential idea was to try and find ways in which we could better understand the reservoir and the hydraulic fracturing process within those reservoir settings, so that we can optimize the completion designs and the spacing decisions, particularly in some of these plays where we have stacked resources and we are not trying to optimize not just laterally but also vertically our well spacings as well as our stage or cluster spacings. And the idea was that the optimization process would essentially make or improve overall unit economics and make some of these projects more commercially viable, especially in the uncertain commodity price environments that we have been for quite a few years now. So the other additional benefit with this optimization process, as envisioned, was that with the reduced number of wells, we would be able to essentially minimize the environmental impact of some of these developments. So I mentioned the HFTS-1 project and the 3 separate phases. The first 2 phases of the project are already complete. I also mentioned the HFTS-2 project in the Delaware Basin. That project has also ended recently. And a lot of this data has already been shared. This includes multiple project reports as well as a lot of actual field data and observations that were released through the EDX website, NETL's data exchange. And we also have a large number of publications, both conference papers and journal papers that have been published over the past 6 years now. And that's also available out there for review. So I'll just go over briefly the test sites in case there are folks out there who are unfamiliar. So we have the HFTS-1 project that I talked about. We had the first 2 phases, phase 1 and phase 2. These were in Reagan County, Texas, targeting the Wolfcamp formation. We had 2 go-through wells at the 2 separate sites. And the idea for both these go-through wells was essentially to capture SRV and to understand far field frac geometry and proppant distribution at those locations. The phase 2 of the project was essentially an EOR project using huff and puff injection of natural gas. The HFTS-2 project, as I mentioned, in Delaware Basin, located in Loving County, Texas, again targeting primarily the Wolfcamp formation. This was the site where we had our 3rd go-through well, essentially sampling the SRV. And at this particular site, we actually collected close to 950 feet of through fracture core across one of the test wells. This site was also different from the first two phases of the HFTS-1 project in that we had advanced fiber optic diagnostics introduced for the first time. In fact, we had 3 separate wells which had permanently installed fibers, and a lot of data was collected, including distributed acoustics, temperature, strain, far field strain, as well as pressure and temperature gauge data. Also, this was the site where we actually carried out first infill ProppantLog for one of the wells, because we had existing parent wells. In this figure here on the top, you can actually see it as the 2 yellow laterals. And because of these existing parent wells and the excellent control we had for the nearby child well, we actually decided to run the infill ProppantLog using drilling mud return samples. The final phase of the HFTS-1 project is another EOR project, but this time it's a liner recompletion. This particular project is located in Jewett County, Texas, targeting the Eagleford Formation. And this was also the site where we actually had our 4th go-through well, essentially an observation well, which also included a significant code interval. And this particular observation lateral was designed such that we could not only sample the far field fractures and proppant from actual data collected from that well, including, for example, this code fracture interval that I talked about, but also we had permanently installed fiber and gauges in this particular well. And the idea was to essentially understand communication with the nearby laterals which were being recompleted or re-stimulated. Again, for this particular infill observation well location, we actually ran a ProppantLog to understand the existing propped frac systems associated with the original completions before we carried out this liner recompletion. So before I move on to some of the observations, I just want to go over some of the key takeaways. And the reason for that is I want to provide an overview of kind of what we are going to go over during this presentation, and therefore situating everyone with some of these key conclusions beforehand, I believe would be beneficial. So one of the most important observations is that the fractures and the fracture characteristics that we observe in a lot of these data sets. So in this particular case, we have 4 different core throughs sampling the SRV. What we observe is that these fracture characteristics are governed by not just the spatio-temporal fracture propagation effects, but also varying rock properties, which also has a very significant role and impacts fracture characteristics. Another factor that seems to impact fracture characteristics is the stress effects within the reservoir. In terms of the proppant distribution, what we observe is that proppant entrapment seems to be a function of fracture morphology, which is what we would expect. But these surface characteristics that are essentially defining the proppant distribution that we observe, while that is the key, that in on itself cannot be used as a means to interpret prop fracture systems. And we have to use other qualified derived parameters from the proppant data itself to actually make qualified interpretations around where the propped fracture systems are. One such parameter, for example, could be relative abundance of larger versus smaller proppant particles. In terms of distribution of fractures themselves, the hydraulic fractures, what we find is the hydraulic fractures are clustered. We do have within these fracture cluster systems what we can interpret as primary fractures and associated secondary fractures. And these fracture systems likely create fracture corridors that we can actually observe far field. And based on the fracture properties, we can also derive certain key attributes of these fracture corridors from these direct far field observations within the core. Finally, because I did talk about a couple of examples where we did run infill ProppantLog using mud return data. So what we can say based on our observations from those two test runs as part of these projects is that the log and the properties or the derived attributes from these logs, they can actually be a very good indicator of, or provide a very good indication of where we have some of these propped fracture zones, and more importantly, where we have unpropped sections. And I'll show some examples of that. And that's important because that helps us identify, especially during infill drilling and completions, essentially targets where we can go in and fine tune our stimulation for those infill wells to optimize our infill completions. Moreover, because we can identify some of these propped zones, we can also potentially interpret how we might be having interwell communication between at those infill locations and some of the nearby pre-existing parent laterals that we may have. So now let's dive a little bit into some of the key learnings. So as I said, I'll go over obviously both observations from the fracture distribution and also the proppant distribution at a number of these sites. But in terms of drivers for both the fracture distribution and proppant distribution, it's useful to actually look at uh, what are our expectations in terms of what those drivers could be. So we know that there are, of course, some first order drivers because we have a pre-existing stress state within the reservoir. So the stress anisotropy or the orientation both have a significant impact on fracture propagation. So that's clearly one of the expected first order drivers. We also have our original completion design. So we have the stage or cluster separations and the cluster designs. And that again, clearly should have an impact on what we are observing far field to some degree. And at the same time, because we are actually sampling these far field locations using some infill sampling wells, the trajectory of these wells and therefore the sampling locations could actually be uh, pretty variable. So we might be actually sampling vertically, we might be actually also sampling laterally. And when we do that, those differences or those variations can also have an impact on what we are observing far field. In terms of some of the some of the second order drivers, of course, we have the stress perturbations, which is dynamic in nature because you'll have hydraulic fractures which are developing or propagating through those far field locations. And when they actually did propagate, they would perturb the stress state, and those perturbations would then potentially impact secondary fractures. We can also expect complexities and impacts on fracture growth, which are driven by lithology or differences in lithologies or bedding. And that complexity also can be a significant driver in terms of the proppant distribution that we observe. So essentially impacting proppant transport, for example, vertical proppant transport. Of course, there are other factors such as biases, but we won't be looking into that. But let's now dive into some of our observations. So one of the things that we have looked at using these far field core through experiments is to essentially look at the fracture distributions far field. So it can be useful to have a mental map of what we may expect in terms of the fracture distribution far field. In this particular example, if we have this well being stimulated with a specific stage design with cluster spacing, and we have this far field location where we are essentially sampling these fractures, when we actually stimulate this well or this particular stage, and we have an existing stress state within the reservoir, we can expect some primary fractures to develop. But with time, because of these primary fracture systems growing within this part of the reservoir, we can expect some stress perturbations within the reservoir, and those stress perturbations then would likely impact any secondary fractures that might grow later on. And those secondary fractures, therefore, we would expect would have certain differences in their characteristics or properties compared to the primary fractures because of the impact of that perturbed stress state. And so that's essentially the mental model that we want to go with, and then try and see if our observations actually match that model or not. So here are some examples of actual um, fracture faces, hydraulic fracture faces from one of the go-through experiments. So in this particular case, we are looking at fractures from the first test site HFTS-1 project in Midland Basin. And what we see is, as I had mentioned in some of the key takeaways, a lot of these fractures seem to occur in clusters. And within these clusters, there is systematic transition in fracture properties. So in this particular case, for example, we are looking at the roughness characteristics of these hydraulic fractures. And we see that the roughness actually varies, or if we look at the transition in the roughness characteristics, it'll vary systematically from very rough fractures uh, to very smooth fractures, or from very rough or very smooth to highly rough fractures to then again smoother fractures. And these transitions can occur within a few feet to tens of feet. And so these observations, these direct observations from the core seem to suggest that we do have a significant impact on stress perturbations on or the developing stress environment within the reservoir on the actual um, um, hydraulic fracture system that we are getting far field. And we have some other observations as well, which also validate this interpretation. For example, systematic variations in orientation of these hydraulic fractures far field. But since we are looking at these hydraulic fractures far field and we have all of these properties, all of their properties mapped out from the core, we can actually look at their clustering behavior. I mentioned that we do observe this clustering behavior where we see these systematic transitions in fracture roughness characteristics. If we map out the fracture roughness behavior as a function of distance of these individual hydraulic fractures away from some um, uh, picked hydraulic fractures. So we can pick these markers or of hydraulic fractures as either very rough hydraulic fractures or very smooth hydraulic fractures, just to see what the distribution looks like. So on the figure here on the left hand side, we have picked out all of the highly rough hydraulic fractures, and what we have done is, as we move either downhole or uphole away from the locations of those very rough hydraulic fractures, we map out what the roughness values for all of the other hydraulic fractures look like as we are moving away. And what we can see is, as I talked about earlier, in this particular figure, we are essentially looking at all of the data from one of the go-through experiments. And we do observe that systematic transition that I talked about from smooth to rough to again smooth hydraulic fractures. But what we can also do here now is we can look at some other parameters for these fracture swarms or fracture clusters. So for example, in this particular case, we can kind of identify that this particular corridor or cluster system, for example, as mapped far field, has a width of approximately 28 feet, for example. We can also use some other simple statistical tools. So for example, autocorrelation function on this roughness distribution and the spatial distribution, and we get similar numbers from such analysis as well. And what we can then do is actually go back and tie it back to what we understand from our original wells or parent wells and completions within the pad. So in this particular example that I showed, this is HFTS-1 Re-frac in the Eagleford. At that infill location, we were equally separated from two nearby parent wells. I've highlighted those notionally here as parent A and parent B. And what we know from the original completions is that the clusters were separated 50 feet apart. And what we are observing in that infill location, as I showed in the previous slide, was a cluster width of approximately 28 feet. What that tells me is that it's quite likely that at least in the sample location where we essentially collected the through fracture core, we have a good match between what the expected cluster spacing is far field and the spacing of these fracture corridors or clusters that we observe at that infill well location. So essentially almost a 1:1 correlation, suggesting that each of those clusters, at least at this location, has been able to generate and propagate a fracture system to that infill well location. Again, since we are looking at the fracture properties, we can actually tie that back to other properties within the well and see if some of the other key drivers that I talked about earlier actually do show a correlation with the observed far field fracture distribution at these locations. So in this particular case, we are looking at the HFTS-1 Re-frac data again, and this is from the core through. And what I have here on the top is the calculated roughness values for all of the hydraulic fractures identified in the core. And since we had a full logging suite across this entire code interval, we can actually look at some of that data to understand variations in lithology. So at the bottom panel here in this slide, we have the gamma or running gamma ray log across this SRV interval that was captured. And what we can observe here are, and I've mapped it out here, these 4 sections where we have these significant changes or bed boundaries that occur within this interval. Those also correlate with not just significantly high roughness values, so fractures which are very rough, but we also see very high fractures that show very high textural roughness, which actually match with obviously the changes that we observe at these transition zones, where we are essentially moving from more shaly sections of the reservoir to more carbonate or quartz dominated sections of the reservoir, or some of those in beds. So what that helps us is tie the far field fracture distribution back to the changes in lithology. And what we have observed from the Proppant distribution is that the actual Proppant distribution also follows the behavior that we see from the fracture properties or distribution of fracture roughness characteristics, where we have these significant transitions in rock properties taking place within our reservoir. We have significant Proppant identified at those sections, which can be tied back to complex fracturing associated across those bed boundaries. In terms of the spatial distribution of Proppant, what we have observed from a lot of our cores is that the far field Proppant distribution can be tied pretty well with the cluster distribution, or the parent well cluster distribution that we are actually trying to map. Here we have examples from the HFTS-1 and the HFTS-1 phase 2 course. And in both these, what we can observe is that the peaks, the local peaks in the Proppant distribution data, they coincide with the location of the clusters in the wells that we are trying to sample. And what we also observe for both of these cores is that these cores were essentially the well trajectories were essentially dipping. So we were essentially moving from above the lateral that we were trying to sample to below the lateral that we are trying to sample. So what we have observed consistently is significant Proppant stop showing at significant heights above the laterals that we are trying to sample. So in this particular case, for these 2 examples, the figure here on the left-hand side, we saw significant Proppant up to about 20 feet or so above this lateral that we were trying to sample, and then it stops. And then for this particular EOR core, phase 2 core, we saw significant Proppant up to about 35 feet or so above the lateral, and then it stops. I talked about the impact of changing rock properties, changing lithology, and we saw the impact it had on fracture properties of hydraulic fractures. But as I said, that in itself can also be tied back to the Proppant distribution. So here is an example from the HFTS-1 phase 2 core. The panel here on the left-hand side shows the changes in the rock type. The middle panel here shows the Proppant log, or the distribution of Proppant across the score. And here we have the effective atomic number just to look at the crossovers. And on the right-hand panel here, I have Poisson's ratio and Young's modulus, again showing the crossovers. And the idea here is to try and see where we have significant changes taking place in lithology, and where we have some of these thin beds in the reservoir. But what we observe consistently, and this is consistent across all of the cores that we have collected, the 4 cores, what we see is that the significant peaks that we see in the Proppant distribution, they coincide with changes in where we have these significant transitions in lithology as we're moving from some of those shale dominated layers or zones to some of the carbonate dominated sequences, for example. And what that suggests to us is that there is a strong correlation, at least locally, between the Proppant distribution and
Yeah.
the fracture characteristics. And that's, again, something that we see in the data. So here are some panels which shows examples of the Proppant distribution, which are in blue, and the fracture roughness values, which are the peak values, red with respect to the y-axis here on the left. And those are these bars here. And what we see is that the Proppant distribution locally tracks the distribution of hydraulic fractures. The rougher the hydraulic fractures, the higher the Proppant counts. And this is across different scales. So it could be sections with very little Proppant to sections with large quantities of Proppant, thousands of particles per gram, for example, here in the middle panel. But consistently, we do see that correlation to hold between these two, suggesting a strong driver of the Proppant distribution, be the fracture roughness. We can actually use or look at the Proppant distribution and try and interpret where the Proppant that we are seeing is actually coming from. It can get a bit complicated when we have very complex settings. So for example, in this particular case, I'm looking at the hydraulic fracturing test site 2, HFTS-2 project, and you can see the map view and the gun barrel view and the side view of different wells in the pad. What are of interest to us is this B3H B6S well pair. The B3H was one of the laterals, and the B6S was the slant well, which was used to capture the SRV core. The B6S is this dotted insert here. And you can see that these two wells, they are pretty proximal to one another where we are sampling. And the idea was to try and sample fractures associated with B3H in the sampling location in B6S observation well. But we also note that there are other wells in the pad. So even in this new development, which are these purple or bluish wells, you have, for example, B4H, another well that was actually fracture stimulated. And therefore, we can always question that the hydraulic fractures that we are seeing at this B6S well location, are they truly associated with B3H, or could they potentially be associated with some of these other wells in the pad? And so what we can do is actually use the ProppantLog and some of the derived attributes that I hinted at earlier to actually interpret where some of the observed Proppant and the associated fracture corridors might be originating from. So the figure here on the left-hand side actually shows the ProppantLog. This is the B6S observation well lateral in map view, and the B3H well is this black, the black curve. And these the dotted inserts here are actually representing hydraulic fractures that are originating from the B4H well and that are intersecting the B3H well. And the reason why we can map this out is because the B3H was one of the wells, which was permanently instrumented with a fiber, and this particular fiber was used to observe the B4H hydraulic fracture stimulation using far field distributed strain sensing. And what we have, what these inserts are actually doing is essentially connecting the location of the fracture stages in B4H and the location where the fractures intersected or were interpreted to intersect the B3H fiber during B4H stimulation. What we see clearly, and so again, as a reminder, with B6S, we were essentially trying to map the fractures or the clusters associated with B3H. But what we can see is across wide sections of this logged interval, we have significant a number of hydraulic fractures associated with B4H, which might be intersecting these sampling locations and then intersecting B3H. And if that's the case, a lot of these locations, a lot of the proppant peaks and the data that we see in the log might actually be associated with fractures or fracture corridors from B4H and not from B3H. And therefore, what we can do is try and see if we can use some of the derived attributes from the ProppantLog to interpret where some of those frac corridors are originating from. So one of the parameters that we can look at, I've defined here as the beta parameter, and that's essentially mapping out how large the relative proppant distribution is in terms of the sizes of the individual proppant particles. So you can see lower the value of beta, that indicates more predominantly smaller proppant particles, and larger the value of beta, that suggests more of the larger proppant particles. So what you can clearly see is there is a systematic transition. Initially, you are actually seeing smaller proppant particles, but then as you move deeper into the sample interval and go below the B3H lateral, you start seeing more of the larger proppant particles. And you can see the trajectory from a side view perspective of the B3H, which is this dotted pink insert, and the core well, which is this black insert. And we can then when interpret the proppant log that I've shown here on the top here. It's the same data that's mapped out in map view here, and this beta parameter. So for example, you have a couple of sections here where the beta parameter is actually very low, but we have these very high proppant peaks, and we can interpret these the associated prop fracture corridors to be more far field, likely associated, for example, in this particular case with the B4H. Whereas we have some of these other peaks in the proppant data and corresponding beta values being very high, suggests to us that some of those proppant peaks and the associated prop fracture corridors are likely more near field or more proximal, and therefore could be associated with the B3H, which we were actually in this particular case trying to sample. And again, we can actually validate this interpretation framework using actual observations from the core again. And this has been also modeled as well. But the idea is that if you are actually pushing proppant to larger lateral offsets, you start seeing dominance of smaller proppant particles versus more proximal or near field to the cluster locations, where you actually see a lot more of the larger proppant particles. And we see that in the figure here on the left-hand side, where you have the lateral offset on the bottom. And you can see that if we are much closer to our cluster locations, we have the 100 mesh or the smaller proppant particles are not that significant in terms of the quantities we observe. In fact, they're very similar to the larger 4070 particles that we observe. But far field, if we double the lateral distance, we are actually seeing an order of magnitude difference in the number of smaller 100 mesh proppant particles, which are these greens, versus the larger 4070 mesh sand particles, which are these browns. So again, it kind of validates the interpretation framework that I talked about in the previous slide. And we can actually look at some other data, especially the fiber data that I talked about, to see what impact that has in terms of our interpretability of the proppant distribution. So as I mentioned, we have this far field log where we are actually able to map the proppant distribution which is this red code interval. At the same time, across these clusters in the B3H well that was being stimulated and that we are trying to sample, we actually have, as I mentioned, an installed fiber. So we can actually analyze the DAS data from the fiber to understand the amount of proppant and fluid that was placed across these clusters. And so in the figure here on the bottom, what I have is for each of these individual clusters, the amount of proppant that was placed as calculated from the DAS data from hydraulic fracture profiling. And the red curve here actually shows the far field proppant as it has been associated with each of these individual clusters, assuming the fracture corridors that I talked about earlier. So once we do that, what we observe is there is a good correlation between the amount of proppant that we were placing at the clusters, which is this blue, and the amount of proppant that we are observing far field, or relative distribution rather of proppant far field. And this good match or good correlation that we observe is in depths where we are very close to the lateral that we are mapping. But as we are moving away, if we have at significant height above or at significant depths below the B3H lateral, you see this wide variation between these two data sets. And that again suggests to us that what I showed earlier, where let me go back, where I showed that above and below the lateral, there might be significant impact of fractures from B4H wells, whereas across stage 19, there is very little impact from the B4H well. The same gets validated using these two data sets as well. And again, at number of these sites where we have these logged intervals, we were also able to put in pressure gauges to essentially monitor the pressure drawdown response over time. And the idea there here was to essentially understand what the drainage pattern looks like, and if possible, to essentially tie that back to some of what we understand from these sampled intervals. So for example, distribution of hydraulic fractures, location of these intervals or these gauges, for example, and so on. So what we have observed once we have analyzed all of these different data sets and the pressure response at these various gauges across this code interval is that the proppant related parameters and the hydraulic fractures, these are some of the parameters that show the most significant impact on that drainage behavior in terms of the correlation. And this is consistent with a multiple observations. So here is an example from HFTS-2, but I also have another example from HFTS-1 Ph3. Here we have two sampling locations, one location with very little to no drawdown. You can see a pressure value of 7,600 PSI, whereas another location with significant drawdown value of about 6,336 PSI of reservoir pressure. And what we see is if we look at the ProppantLog associated with these locations, at the location where we had significant drawdown, we have significant proppant or prop fractures identified, whereas at the location with almost no drawdown, we have almost no proppant. And these proppant log observations can then be also tied back to fracture distribution if we have that information. So for example, at this location where we had very little proppant, we actually have the code interval. So when we look at the core, we actually see that the very little proppant actually correlates with almost no or negligible hydraulic fractures across that interval. So across multiple data sets, we have been able to validate the ProppantLog as a good proxy to be able to understand drawdown behavior. So I talked about ProppantLog used on different cores, but we can also use it for infill wells where we essentially collect mud return samples and run the log using those samples. Here is an example from the HFTS-2 well where we had one of these infill child wells. And the idea was to try and see how the proppant distribution looks compared to the pre-existing parent wells. You can see the pre-existing well laterals here in green. We also had a pair of northward facing laterals up here. You can see them on the right-hand side here and on the map view as well. And what we observe is there is significant proppant associated with both these corridors or expected corridors associated with two sets of pre-existing parent wells. But what's also interesting is if in the south corridor associated with these BR parent wells, you see that the proppant distribution is very uneven. You have the absolute tail end with significant proppant, but then towards the middle, not a whole lot of proppant or propped fractures being identified. So we can actually go in and look at some other data sets that were collected as part of this project, including crosswell strain that I talked about, microseismic data, including source mechanisms or moment and inversion, OBMI log, etc. And what we observe is the overall propped distribution of proppant or abundance of proppant. It matches with the conductive fractures from the OBMI. But as I mentioned, these two sections or these two separate zones that I talked about, they can obviously be clearly seen in the ProppantLog data using the panel here on the left. What we also see is in these two sections, if you look at zone B, that's essentially a zone where you have more significant fracture growth towards this pre-existing parent wells, and that's the reason you have less of fracture growth westward towards the B3H, which is one of the newer wells, whereas in zone A, you have less preferential fracture growth towards the pre-existing BR1H, BR2H, and more preferential fracture growth seen here by larger or more fracture arrivals from the crosswell strain data or much higher cumulative strain response, for example. So here is another example from HFTS-1 phase 3 where we can actually tie the proppant log to the crosswell strain response, specifically the strain change rate, where we can observe, for example, during one of the wells being preloaded, the interwell communication between the sampled infill well locations and the preload well, and those fracture communication or communication zones correspond very strongly with where we have peaks in our ProppantLog data. Just some potential use cases for the log itself. So I talked about ProppantLog. In case of re-stimulations, it's very intuitive how you place your new fractures, but especially when it comes to infill drilling and new infill wells, optimizing spacing for fractures can be a challenge, and therefore this technique can be a good method or key indicator for prop sections, and therefore can be used to optimize your infill completions. We have found that sampling rates as high as even 90 feet can actually be adequate in understanding unpropped sections, and therefore can be very useful. It's a fail-safe logging technique because we don't really have any instruments being put down hole, so it doesn't really matter if we have high pressure, high temperature conditions. And also it's very easy and significantly cheaper to run and acquire compared to traditional wireline logs. And it can also be used in very complex environments, as I showed with the example from HFTS-2 side, where you may have multiple tens of wells, but the log can still be used to essentially understand what the propped fracture system or propped fracture corridors associated with some of these other wells look like at those locations. So finally, some of my conclusions. Obviously, I can bin them kind of into these developmental, design, and surveillance related key learnings. So in terms of developmental, I mentioned this, we do see some significant significant uh, uh, issues with vertical proppant transport. I wouldn't really say issues in terms of just the absolute observations. We see that the vertical proppant transport, at least significant proppant, seems to be depth limited. That has certain associated questions around the prop fractures, especially above those zones, and how those are relatively moderately propped sections might be producing, and what the production behavior and the mechanisms associated with that production might look like. And also the data itself, because it's actual ground truth data from sampling, might be a useful data set to validate, for example, fracture propagation models or even proppant transport models. In terms of design, we do see that far field these fractures are clustered, and we can actually, as I showed, identify cluster properties associated with these far-field fracture clusters. And those, in fact, can then be useful in terms of how we design our completions moving forward. And in terms of surveillance, I talked about ProppantLog as a very valuable tool and how it can be used for essentially understanding undrained or unstimulated sections of the reservoir at infill locations. So thank you very much for listening in. And thanks to also DOE and NETL for the support, and all of the members of the HFTS-1 and HFTS-2 projects for providing valuable help in making this project successful. Thanks.
All right. Thank you, Dave, for your very interesting presentation. So now we're going to chat, and we have a few questions. So the first question is from Eddie Seabreeze. And so what he's asking is the following. So the visual observations of lithological transitions versus proppant distributions, right? So have you, have you quantified this correlation statistically to check if relevant?
Yeah, that's a good question. So in terms of occurrence, we have checked it statistically, and it's a very strong correlation indicating a strong relevance. However, in terms of magnitude, it's a little bit more complex. So it's when it comes to magnitude, there are other factors that come into play, and some of those factors include, for example, fracture orientations, actual fracture morphology, and the proximal fracture system within those clusters. So there are other factors involved, but as I said, in terms of occurrence, there is a strong correlation.
Okay, so the next question is also from Ed Seabridge. So what MVAR model software did you apply to estimate variable significance? Be careful of looking only at variable importance, such as just to also test model predictively.
Could you repeat the question? Is the question what model we used?
What MVAR model software did you apply to estimate variable significance?
Okay, so the method we used for that analysis, I believe, was a regression tree, and the parameters that we picked up were essentially a lot of let's say rock properties or parameters derived from rock properties, also parameters from which are essentially location or position dependent. So essentially location of the gauges with respect to some of the other wells, and also some of the direct observations or indirect observations, including, for example, logs or proppant distribution or derived attributes from proppant distribution and so on. In terms of the data set, one of the big challenges is that this is a smallish data set because we only have a limited number of pressure gauges. And so what we did was we synthetically extended the amount of data we had to actually run that regression analysis or regression tree. For the second example that I showed, where we were looking at the phase 3 data, we were essentially comparing ProppantLog with the far field strain response or the strain change rate at the fiber. And so therefore it's essentially a direct observation. And because we were seeing a good correlation there, we have good confidence in some of the other observations we have made with pressure gauge data.
All right, thank you. So the next, actually more like comment from Uno. So he really enjoyed the presentation, and especially this correlation of proppant peaks with interbed or interface boundaries. And so, I mean, I'll just follow up on this. I mean, I also, found it very interesting because, maybe you can have some sort of like ledges forming at these interfaces, maybe narrow zones, which can capture proppant. Maybe you can, say a few words about this. I mean, about this observation.
Yeah. So as I mentioned, one of the key things that we have observed is significant proppant in terms of actual measurements or actual sampling. We do see significant proppant where the associated fractures have significant complexity. So the proppant log that I shared here in my presentation today, this is not direct proppant measured from actual fractures. What this is the proppant that's collected from the fracture cores or the core tubes. And so these are maybe 3 feet core intervals or core tubes. So it's essentially representative of proppant associated with all of the fractures within that 3 feet tube. But when we have actually looked at proppant entrapped within real hydraulic fractures, which we have some examples of in these cores, what we observe is where we have very thick proppant packs, and we can see that in the actual core, and we can also see that in the image log. What we have found is the associated hydraulic fractures where this proppant was entrapped, they have significant surface complexity. And more often than not, this complexity is propagational in nature. So you would have twist hackles, stair-step features or plumo structures and so on. And you'd also see more surface roughness characteristics associated with the lithology. Typically, this happens in more carbonate-rich sections of the reservoir, for example, debris flows and so on. And those are the sections where we would see some of these thick proppant packs.
Okay, thank you. And so we have one more question from Jar Mark. And so his suggesting that the difference in roughness that you observed can be related to the fact that some fractures are natural and some are hydraulic. And so the question, his question is how many of the fractures observed actually natural and how many are hydraulic, and so how many fractures are oblique to the SH max direction?
Yeah, so I apologize for that. I should have put some slide in there to differentiate, but all of the fractures that I've shown and all of the interpreted properties that I've shown are for hydraulic fractures. And the way we do that is essentially once these cores were collected, we got them at CoLab. We had a team led by Dr. Gale from BEG, which actually did a fracture characterization workflow on these cores. And the idea there was to essentially go in, look at individual fractures, identify which are natural, which are hydraulic, separate them out, and then get all of the properties out. So for example, orientations and so on and so forth. So all of the fractures that I show here are all hydraulic fractures, and therefore the correlations are also with respect to only hydraulic fractures.
All right. Thank you for your answer. And so the last is more like a comment from Mohammed Solomon. So it basically says that it's very interesting projects and thanks to you for presentation. So it is hard to disagree. I mean, all the presentations related to field data indeed, very interesting and very, very useful. So so thank you. And we have last chance question from the audience if anybody is willing to ask a question. And so maybe wait for 10 seconds while you type in and see.
Yeah, this is Ali Danishi. I have read your papers, and I have to tell you that reading the information which is in the papers, I wasn't really able to conclusively agree with your conclusions. And I would suggest that maybe more information is needed in order for us to clearly see how you are deriving your conclusions that are important that you have discussed in the paper.
Okay, yeah, that's a fair point.
Okay, thank you, Dr. Danishi. Okay, so I think since we don't have any more comments, this concludes our talk today. So thanks, Dave, again, and let me